Hi, everyone. So this is a hands-on tutorial for the mixed thermoelastic problem. And yeah, for this, we would need to go to the directory called mixed thermoelastic in the from the parent directory with all the tutorials, with all the hands-on sessions for the school. And here in this folder for mixed thermoelastic, we have some additional directory with the config files, but you don't need to look into that. Those are just technical files needed for running the simulations. What you really need is the notebook, which is provided over here, this thermoelastic notebook. And again, very similar to the other tutorials, other hands-on sessions in the school, this notebook follows very closely the lecture. So I invite you to look into that. Okay, so what I'm seeing already over here is there's some issue with the numbering of equations because these two equations have a number 1. So if you see something like this, you can press this button over here and it will recompile the LaTeX for all the formulas, and it will ensure that the numbering is consistent and the all the referencing, like for example here, is working correctly. The hyperlinks are working correctly in this notebook. Okay, so once you're all set, you now well, we can look into the parts of theory. It just presents the same way, in the same way as in the lecture, the cases of one-way and two-way coupling for the thermoelastic problem. And I emphasize again that we're going to look into the only case of the one-way coupling, which is also called linear thermoelasticity. This is the case when we have a constitutive law in this form shown over here in this equation 1, when the actual stress depends on the actual strain and the thermal strain, which is computed from the difference in temperatures when the body is being heated up or cooled down, and the thermal expansion coefficients, which defines what kind of strains will appear, either corresponding to the expansion or to the contraction of the body due to this heating or cooling. So as we can see, the actual stress depends on the change in temperature, but in the one-way coupling, the temperature does not depend on the actual strain. So that's why it's called one-way coupling. Only the thermal problem affects the elastic problem, but the elastic problem does not affect the thermal problem. So this is what we are going to consider this tutorial. So then we have the strong form of the equations. Yes, we have the balanced linear momentum for this actual stress tensor sigma. We have the thermal conductivity problem, where we have the time-dependent problem. So we don't solve dynamics for the elasticity, we solve quasi-statics, but for the thermal problem, we solve it as a time-dependent problem. Hence, we have this derivative of time over here, and C is the volumetric heat capacity. And then this part over here is what constitutes the balance of energy, of heat energy for the heat conductivity equation, K being the conductivity coefficient. And so we have these two equations for the elastic problem and for the heat conduction problem. And again, the coupling between the two is enforced through the constitutive equation for according to which the actual stress, which is the part of this equation over here, depends on the temperature through this relation given over here. Then we have the boundary conditions. So okay, the same potatoes as were in the lecture. Again, those are not two bodies. We are looking into one body omega. It's just that I had to find a way how to define the boundary conditions for the two physics which exist in this problem, in this thermoelastic problem. So we have directly boundary conditions for the displacement and for temperature where they are prescribed. And then we have the part of the boundary where the traction is prescribed and where the heat flux and the normal heat flux is prescribed. And then also since the thermal heat conduction problem is time dependent, we need to define the initial value of temperature in the whole domain. Okay, so this is the strong form, and then we're going to compare the standard weak form and the mixed weak form. So the standard weak form follows usual derivations, where we have when we integrate the first equations after multiplying them by test functions, integrate by parts, and we arrive at these equations over here. The two unknown fields, the vectorial field U for displacements, it's in the space H1 for square integrable functions, which has the first derivative being square integrable 2, and then the temperature field T, the scalar field, also in H1 space. And then the mixed coupled weak form follows over here. And then in this case, we have three equations for the three unknown fields. We have this auxiliary field Q, which is in H deep space. And then the field U is still in H1 space. And the field T is in L2 space. And so what this means? It means that for the elastic part of the problem, we're using the same exactly formulation as the standard one. Yeah, it's the same equation. This equation 3 and equation 6 are exactly the same and they're identical. And this the unknown field U is being sought for in both cases in the space H1. So when we look into this coupled problem, for the elastic part, in both cases, we consider the standard weak form. However, in case of the mixed formulation for the heat conduction part of the coupled problem, in this case, we can consider the mixed formulation. And this is very similar to what we did in the Poisson problem, in the mixed formulation for Poisson. So I invite you to look into that lecture, that part of the lecture and the associated hands-on session, which explains how we construct a mixed formulation for the Poisson problem. Because here, for the heat conduction problem, is an extension of that idea. So that instead of one equation for the heat conduction problem, we have two equations, and the unknown fields are different. So we're looking into the temperature field in L2 space. So we don't assume that it has derivatives, and then the vector Q is vectorial field for the flux, and it has only derivatives such that we can compute the divergence. So divergence is square integrable for this field. So there are several different properties of this mixed formulation regarding the boundary conditions. I invite you to look into the lectures to look into those details. This is not the focus of this tutorial right now. So we continue to the example. So our idea is to see the things which we saw in the lecture in the example here and be able to play with that. So we are looking into the case when we have a plate with a hole, and this plate has two different materials, and then it's being heated up, and there is no mechanical loading on this plate. Only thermal loading, and all deformation is happening due to the difference in temperatures in the heat conduction problem. So, and the reason why we are considering two subdomains, two parts of this plate, because we want them to have drastically different mechanical and thermal properties, and all that is needed to construct a solution with low regularity. And we will see in detail what that means a bit below, but for the moment, I just want to highlight that so this material 1 is hard, has a high value of Young's modulus, and has high value of the thermal conduction coefficient. So the heat is going to go quite quickly for this material 1, while material 2 is soft, has a lower value of the Young's modulus, and it has a much lower thermal conductivity coefficient, meaning that heat is going to conduct very slowly through the domain 2. So all the other parameters are the same, and the initial temperature of this whole plate is 0. And then we have 0 temperature boundary conditions for the domain 2 at the outer surfaces. And then on the inner surface, we have 1000 degrees applied. So as you probably can see, the boundary conditions are symmetric, and therefore, and geometry is symmetric, and therefore we can just consider a quarter of this plate. So we impose additional boundary conditions for the symmetry that at this boundary over here, we have 0 horizontal displacement and 0 horizontal flux. And similarly, at this boundary over here, we have 0 vertical displacement and 0 flux. Okay, and well, the idea with this boundary condition, what you can imagine is that initially the whole plate is at 0 degrees, and then we do something like flash heating to heat up this surface over here to 1000 degrees. And what's going to happen, like in the first few seconds after the simulation starts, is that the heat will very quickly propagate through this material one. It's going to heat up this circle domain over here, but it will struggle to propagate into material two because the conductivity in material two is much lower. And also the boundaries of the material two are exposed to the zero temperature on this outer parts of the boundary. And therefore, we're going to have a huge jump of temperature between domains 1 and 2. This is what we mean by the solution with a low regularity. And we're going to look into what's going to happen in this interface. In particular, we're going to look into this point symbolized by a star, where with those coordinates over here, which are relevant to the coordinates of the whole domain. And this is where we're going to check the solution of all the three fields to see the convergence. Okay, so we can start with this notebook. So what you can probably already see over here is that the structure is very similar to the other notebooks, and we have first a cell where we just need to import necessary modules, but we can close the cell later on because we would not need to be changing anything there. And the next cell is defining some utility functions for mesh generation. We are using Gmesh library. Then we define the function which is going to call MoFEM. In particular, it's going to be command line calls to MoFEM executables, MoFEM binaries, and we pass the parameters through the command line. And finally, we do post-processing. We visualize the results using PyVista and IPyGenie backend. But all those are just details for those of you who are interested in these libraries. But if you're not, you can just execute the cell and hide it because you would not need to look into it during the tutorial. This is not the point of the tutorial at all. This is an important cell where we define a dictionary with all the relevant parameters for pre-processing, for the solution, and for post-processing. And some of these parameters don't really need to be changed, like the side length of the plate and the hole radius. This is going to just define the mesh dimensions, and that's not something that we ask you to do for this particular problem, the same as interface radius. But what we will be changing, we're going to be changing the element size. You can also try to play with the type of the mesh. Is it quads or triangles? We're going to be able to run two different methods, the mixed one and the standard one. And so this simulation is a bit more heavy computationally than the Poisson, which we considered just before. And here you might want to use more processors if you can. And then approximation order is the approximation order for the field temperature. And in the mixed simulation, the fields Q and U will have order P+1. It's just for to let you know, but you will be just controlling the order by one parameter. And finally, here is the point where we're going to be evaluating the field for post-processing for the convergence test. But yeah, you can feel free to change it if you're interested. Okay, and with all these parameters set, we can now try to play with generating the mesh and computing the results for the mixed and for the standard formulation. So let's start with setting the element size 005. So we're going to have a rather coarse mesh, like about 20 elements per side. Sorry, 10 elements per side of our domain, of our quarter of the plate. Yeah, so here, this is what we're doing. So, well, the mesh is not structured. It's a bit finer around the zone which is close to the hole and in the interface. But in general, we more or less control the mesh size everywhere by this one parameter. And now we're going to run the simulation for the mixed formulation. We're going to choose the order one, but I invite you to try higher orders to get the results, but it's just that it's going to run for a longer time. So I want to try with the simpler case at order one. And similarly, we're going to choose the same mesh and the same order, so the same element size and the same order for the standard formulation. And we will try, we'll run it again. and see the output. So it takes a bit longer to run. You might need to wait. Well, actually, for this coarse mesh, it's quite fast. It's the final mesh will take the final mesh will take a bit longer. Okay, so we can visualize the results now, and here is probably what you would see. So here we're looking into the results for the mixed formulation, for the standard formulation. And you can choose which fields to look at. So here, well, here I give you how the names are called in the executables of MoFEM, which run the mixed formulation for this problem and the standard formulation for this problem. So if you want to look in temperature mixed, you choose T, flux for flux and so on, and then for the standard formulation, you can look into time, temperature displacement, displacement gradient, and stress. While for the mixed formulation, you can look into the temperature, flux, displacement, strain, and stress. And temperature is a scalar field, so we're just looking well into the only component there is. We are warping the mesh by the displacement field. You can switch this off if you want. You can put this warping factor to 0, and then there is no the fields are still there, but the deformation of the mesh is not shown. But I think it's a good way how to visualize how the mesh is being deformed due to this difference in temperature. In the same way, you can look into having edges shown or not. Okay, but probably what I wanted to say over here is that the solution looks quite coarse, both in case of the mixed and the standard formulation, and it's not really satisfactory. Well, that's expected with the mesh that we consider for this particular problem, which has quite a complex solution. So we're going to look into a finer mesh. So I set the mesh size here for the mixed problem 2 times smaller elements. So I regenerate the mesh. Yes, here how it is. And I rerun the analysis for mixed, and then I set the same mesh size for the standard, and I rerun the analysis there. Okay, the mixed done. Now the standard running. So for this finer mesh, it's going to take a bit longer, but still a reasonable time. Yeah, you should see the results in under a minute, probably even faster. Okay, so there's, the output files have been converted, and we can now see at the results. And they look now much smoother, especially the mixed formulation case. Yeah, the one shown on the left. A much smoother solution shows us how the temperature is dropping from 1,000 to about 250 or something close to this interface, and then we can see how the remaining of the domain is exactly at 0. While in the case of the standard formulation, we see this very non-physical zone where we have the temperature being about -10 degrees. Well, as you can probably see for the mixed formulation case, there's also a case of negative value being the minimal values in the domain, but those are values of the order of 10 to the power -1, while here there's negative values at 10 to the power order 1, so 100 times greater negative values. And of course, negative values are non-physical. For this particular problem, the values should be between 0 and 1,000 everywhere. But well, those negative values are here, the standard finite element error, which we'll always have. While in this case, it's on top of this finite element error, we have instabilities. We have those oscillations caused by this lower regularity of the solution. If you're interested, you can look into the other fields, like the displacement field. Like I said, displacement is vectorial, so you can look into the different components. So we're looking at X right now. Now we're switching to Y. You can look into even the strain field and then you have to choose the displacement gradient name over here. So, okay, that's probably XY term. If you want to look into the X term, you need to choose the component 0. So the numbering is standard 0, 1, 2 for the directions of vector, and from 0 to A to tensor with the standard tensor notation, like in Paravium. So we see that the results are quite similar. It's the temperature which is standing out in the difference between these two results. To understand this better, we're going to do now the convergence study. So remember, there was a point of interest that we defined over here, very close to the interface between the domains, and you can change this point where we're going to be evaluating the results if you want. But here we just selected that point, and we're going to consider three meshes. Yeah, the first two ones are the ones that we run analysis with, and the third one is even a finer one. And we're going to look into a series of plots of how the mesh convergence for temperature, displacement, and strain takes place. So I'm going to just start this analysis. It takes a while, so I'm going to pause the recording and come back when it is ready. Okay, so this cell over here has completed working, and we can do the plotting. So we're going to be comparing the convergence of the mixed and standard formulations with the decreasing element size that we were doing these computations for. And the first plot is going to look for the how the temperature is changing with this, well, with the different element size. And we can see, so remember that we're talking about the temperature at this point of interest at this step over here. So that's the temperature in this domain somewhere over here. So it should be close to zero. No surprise that it's zero. And we are at zero value for the mixed case. For the standard case, is jumping around. You could say that it's slowly converging to zero, but it's oscillates, so it's like above 100, and it's below minus 150, and then yeah, you can see what's happening. So probably there would be a need for more steps of this refinement to get a better solution for the standard one that are going to get closer to actual zero. While with the mixed formulation, we are getting zero all along, thanks to the properties of this mixed formulation that we discussed in the lecture. Similarly, if we look into the convergence for the case of the displacement, again, well, the results for the mixed are changing a little bit from the coarsest mesh to the finest one, but much less than for the standard one. Like surprisingly, for the standard one, the result with the intermediate mesh is quite close to the result of the mixed one, but then goes away. So I hope these three cases, these three plots over here, they reinforce the idea is that it's not only that we have something weird happening at the interface between those two subdomains in the case of the standard formulation over here, but then like the zone of the negative values will be there even if we try to refine the mesh. So we would need to go for extremely fine meshes between the interfaces between those two domains to actually recover the values of the fields in a standard formulation close to the values produced by the mixed. So that's all what I wanted to show in this tutorial. Let me know if you have any questions. Thanks and bye.